Okay, in this video we will look into the lead compensator in control system. The question here we got to deal with is design a lead compensator for a unity feedback system with open loop transfer function g of s is equal to k over s of s plus 1 into s plus 5, and we need to design that lead compensator in order to get the velocity error constant kV greater than or equal to 50 and phase margin greater than or equal to 20 degree. Okay, now find K. Given that velocity error constant is greater than or equal to 50, but take that as 50. Kv is equal to 50. So Kv is equal to limit of s tend to 0 s of g of s, and from that equation we can find out the value of k as kv is known. And here we are using the Bode plot method. So next steps are for designing the Bode plot, given that g of s is equal to k of that, and we are standardizing the equation. Okay, and we will get finally 50 by s of 1 plus s into 1 plus 0.2 s, and we will substitute j omega for s in that equation, and we get two corner frequency here. Okay, first one is 1 radians per second, and next is 1 by zero point 0.2, which is 5 radians per second. That we get from here. We got j omega in the first term, or is 1 plus j omega, and in the second one we have 1 plus zero point 0.2 j omega. So the corner frequency will be like the reciprocal of first one, because first coefficient is 1, so it's 1 radians per second, and in the second term we get the coefficient of omega as zero point 0.2, so 1 by zero point 0.2 will be the corner frequency, so that is 5 radians per second. And we'll go for writing the table. First term is we're taking as at 50 by j omega, and its slope is, yeah, j omega is in the denominator, so as j omega is in the denominator, where the slope will be minus 20 dB per decade, and the other term is 1 by 1 plus j omega. Here also the j omega is in denominator, so it will be minus 20 dB, and its corner frequency is 1 radians per second. And now the change in slope, minus 20 plus minus 20, that is minus 40. And another term, yeah, similar things have been there. Change in slope is equal to minus 60. And usual steps, okay, choose a low frequency omega L which is less than the omega C1, I mean less than radius, sorry, 1 radians per second, and choose another frequency omega H which is greater than omega C2. Here omega L is equal to 0.5 radians per second, and omega H is equal to 10 radians per second. And now we want to find the gain in order to plot the magnitude part of Bode plot. So at omega is equal to omega L, gain is equal to 20 log of the first term, that is 50 by j omega, and omega here is 0.5 radians per second. So gain is equal to 20 log of 50 by zero point 0.5, that is 40 dB. And when omega is equal to omega c1, that is 1 radians per second, gain is equal to 20 log of the first term, 50 by j omega, 20 log 50 by 1, that is 34 dB. And now when omega is equal to omega c2, that is the second corner frequency, the equation has a little change, that slope from omega c1 to omega c2, that is, we have already found out that it is minus 40 into log of omega c2 by omega c1 of it, that is log of 5 by 1, plus the gain at omega c1, that is 34 dB. So minus 40 into log of 5 plus 34 is equal to 6 dB, and thus the gain at omega is equal to omega h, the similar same equation, and we will get minus 12 dB. So the uh, factors to be needed to draw the magnitude plot is over, and next we want to find out the values to upload the phase plot. See, this is a phase plot equation. Phi is equal to minus 90 degree minus tan inverse omega minus tan inverse 0.2 omega. See, why minus 90 degrees? That we have a j omega term, that is a constant j omega term at the denominator, and we has the 1 plus j omega and 1 plus zero point 0.2 j omega at the denominator. That's why minus 90 degree and minus tan inverse omega and minus tan inverse zero point 0.2 omega. So substitute the values of omega in this, and you will get the corresponding phase angle and draw it in a semi-log sheet. So we will get the bode plot. Okay, after drawing the bode plot, we need to find the first phase margin of that. Let phi this is equal to phase of g of j omega at gain crossover frequency, and omega is the phase margin of uncompensated system. And from bode plot of uncompensated system, we get phi g is equal to minus 224 degree. So this is a bode plot. See, it has both compensated and uncompensated uh, magnitude plot and phase plot. First, we will look into the uncompensated. This is the magnitude plot uh, of uncompensated system, and this is the phase plot of uncompensated system. And now the 5GC that I was talking about is a phase at um, omega GC, that is at gain crossover frequency. See, let's see when the magnitude plot crosses 0. Yeah, at this point magnitude plot crosses 0, that is 0 dB, 0. So below that, look at the omega GC. You can find omega GC at that point, and it will be some. See, omega GC is not important here, so that's why it is plotted like that's omega GC. It will be something, a value near 7 radians per second, and corresponding to that we will get the minus 224 degree. That's the gain crossover phase value, that is 5GC is equal to minus 224 degree. That's what we have here. 5GC is equal to minus 224 degree, and phase margin is equal to, that's you all know about, phase margin is equal to 180 degree plus 5GC. So we will substitute the value for 5GC here, and we will get the phase margin of the uncompensated system. So after substitution, we can find that the phase margin is negative 44 degree. So if the phase margin is negative, it is mean by it is meant that the system is unstable. So the point is, if the question is not saying what kind of compensation that you need to do to the network, just from at this point you will understand what type of compensation does it needs. That unstable systems, we can only apply we, that was a wrong statement. So, okay, for unstable system, a phase lead is the required one. So we need to use lead compensation here, whether it is not stated in the question. So we need to have a phase margin of 20 degree. The specification was in the question. Okay, we need 20 degree of phase margin. And now uh, we need to find phi m. See, phi m is the maximum lead angle. So desired phase margin is 20 degree, and the equation of phi m is equal to uh, desired phase margin minus the current phase margin of the uncompensated system plus an error value of 5 degree. So that's what we have done here. Phi m is equal to uh, 20 degree minus 44 degree plus 5 degree, that is equal to 69 degree. But the lead angle, the maximum lead angle cannot exceed the 60 degrees. So we need to have two uh, lead compensator cascaded with the g of s in order to give the compensation. So we need phi m is equal to 69 degree divided by 2, 34.5 degree. We need compensator with lead angle of, we need two compensators with lead angle of 34.5 degree. Determine that alpha, the transfer function of lead compensator, alpha is equal to 1 minus sine phi m 1 plus sine phi. We get phi m 34.5 degree, and we will get 1 minus sine 34.5 degree plus divided by 1 plus sine 34.5 degree. That's alpha is equal to 0.28. See, this is the basic equation for a lead compensator, that is Gc of S is equal to S plus 1 by T divided by S plus 1 by alpha T. So in order to find out the transfer function of Gc of S, we need to find alpha. Okay, alpha is equal to 0.28, and from the Bode plot we need to find the dB magnitude corresponding to omega m, where omega m is minus 20 log 1 by root alpha. It is equal to minus 5.5 dB. So from the Bode plot of uncompensated system, the frequency omega m corresponding to a dB gain of minus 5.5 dB is found to be 7.8 radians per second. Now about the value of t. See, we need the value of t because it gives us the zeros of the lead compensator. Uh, t is equal to 1 by omega m root alpha is equal to 1 by 7.8 root of 0.28 is equal to 0.24. So transfer function of the lead compensator, Gc of S is equal to S plus 1 by T the whole square divided by S plus 1 by alpha T the whole square. See, why this whole square is that uh, there are two lead networks that we are using here, because the maximum lead angle is 60 degree. So we need to use uh, two lead networks, as I said earlier. So that's why as they are cascaded in series, both will get multiplied and we will get that square value. So that's what the square here. Okay, that's all about lead compensator. We get the transfer function of lead compensator, and just put it series with the g of s, and the system will get compensator.